Start Chandini.
Good morning everyone. I am Dr. Chandini and I want to give a lecture on the topic buck boost converter tuning, and the optimization technique. What we have used is the strategy is optimization techniques. So when coming to the block diagram of a buck boost converter, so mainly what we have to discuss is what is a buck boost converter. A converter which converts a DC voltage or current to a DC voltage or current with respect to the duty cycle. So that is the main basic operation of a buck boost converter. So here in this buck boost converter we are having a DC supply as input and a MOSFET, and a MOSFET is driven by a diode, and this diode is connected to the inductor and a capacitor, and here we have taken the R load. So here the R is nothing but the resistive load, and here L is nothing but the inductor and the C is nothing but the capacitor. So basically whenever the MOSFET is nothing but metal oxide semiconductor field effect transistor. So it is called a switch and it is a control switch. So whenever it is driven by a pulse width modulation technique, generator pulses, so that the MOSFET will be operated. So whenever there is a switch on condition, in on condition the inductor will turn on and the inductor will get charged, and as well as the capacitor also will get charged. And during the off condition, here the diode D1 helps us to block the current from the load side to source side. So the main drawback of this basic diagram is the output is always dual dependency nature and always negative. So dual dependency nature means whenever the input increases, the output also increases, and whenever the input decreases, the output also gets decreased. So we can overcome this issue by using some parallel buck boost converters technique. So what do you mean by a parallel buck boost converter? So nothing but the converters are connected back to back in parallel. So the same inductor is connected with respect to this diode D1 and diode D2. Okay. So here diode D2 helps us to block the currents. What are the currents coming from the output side? So it will block the currents to the input side, so that the input source ripple content will be reduced. So what do you mean by ripples? Ripples are nothing but whenever there is a MOSFET switching, so some voltage will get into some values, so which is not acceptable, permissible limits. So that this is the main basic notation of the ripple content. Ripple content is nothing but the disturbances of the voltages. Okay, so that output voltage which will be get disturbed. So if we are not getting any voltage accurately, so what will be happen? The output it cannot be used for any application. So here we are designing the C2 capacitor. We are connecting C2 capacitor and as well as C1 capacitor here, all with respect to the C1 capacitor. So what will C2 will do? It will charge whenever there is a extended ripple content in the circuit. The C2 capacitor will get charged. So after C2 capacitor will get charged, then there is no point of coming of current from outside, load side to source side. So this is one of the technique which we are using for blocking the ripple content in the input side. Okay. And next the optimization. Here already we have mentioned that the optimization techniques. So here in the optimization, what optimization techniques we are using? So some of the AML, deep learning techniques are inculcated for optimization of the buck boost converter parameter tunings. So what are the parameters we are tuning here? Mainly the duty cycle of the MOSFET, and second one the inductor and capacitor values, and not last but not the least, we are tuning the efficiency and the power quality of the ultimate output. So this is what we are getting. The optimization techniques can be discussed later, so that we can use so many optimization techniques, which is CSE part, like computer science AML part. So this AML and computer science part also can be associated with power electronics, so that we can optimize the buck boost converter parameters. So this is what my lecture on. Thank you.